Welcome to section 3.2, Transformations of Functions. Please consult the notes. On page 41, you'll see several definitions explaining exactly how the shifts that we're going to see in this section will work. The first shift, or the first transformation rather, that we'll look at is the vertical shift. So if we start with a function that we know about, say f of x equals x squared, here I'll construct a table. We won't always need to do this once we understand how these shifts work. So if I square 0, I'll get 0. If I square 1, I'll get 1. Squaring 2 gives us 4. Squaring 3 gives us 9. We know all of these points from the discussion of the basic functions back in 3.1. But now we are going to take those outputs and we're going to add 2 to find points on the function g of x. So negative 3 squared gave us 9. If I add 2 to that, I get 11. Negative 2 originally gives us 4. If I add 2 to that, I get 6. Negative 1 gave us 1. Adding 2 gives us 3. 0 squared gave us 0. So 0 squared plus 2 would be 2. And we can continue in that fashion. Notice that we're taking the old output, f of x, and we are just adding 2 to it. We can do the same type of thing for the function h of x. In this case, we're going to subtract 1 from every x squared that we got originally. So 0 squared minus 1 would give us negative 1. 1 squared gave us 1 originally. If we subtract 1, that'll put us at 0. If we square 2, we get 4, and subtract 1 gives us 3. Squaring 3 gave us 9. Subtract 1 to get 8. And going in the other direction, we see similar behavior. So with this table, we can then attempt to graph this set of functions. Give ourselves a nice big axis to work with. Okay. So if we have 1, 2, 3, 1, 2, negative 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's about as high as we'll need to go. Remember, we're going to graph f of x first. That's one of our basic functions, so that's one that we should be able to graph very easily and quickly. This one's also even, so once we graph everything to the right of the y-axis, we can just mirror that across to find the rest of the function's graph. That's one of the advantages of knowing that a function is even. There we have our lovely parabola x squared. And we'll label it f of x. Now g of x contain the points 0, 2, 0, 2, 1, 3, 2, 6, and 3, 11. So we can see how every single point that we knew about is just being shifted up by 2 units. And again, this graph has that symmetry that we saw, so we can reflect all of those points across and get the rest of our picture very quickly. So there we have g of x. Now h of x is going to involve going in the opposite direction. If we put a couple of points below the axis, that'll help. So 0 gave us an output of negative 1. So if we plot the point 0, negative 1, it's going to be on the y-axis. We got the points 1, 0, and negative 1, 0. So those will be our x-intercepts. We also have the points 2, 3, and negative 2, 3. Oh, that should actually be up a little further. We have the points 3, 8, and negative 3, 8. So there we go. All of our graphs, and they look pretty much identical, but only different in their position on the xy plane. So there we have h of x graphed below f of x because we shifted down 1 unit, and g of x above our graph of f of x because we shifted it up 2 units. So that corresponds with that first definition, which says that if we simply add a constant or subtract a constant, we can find the graph of our new function by basing it off of the graph of our old function and simply shifting by however many units we are adding or subtracting. Adding moves us up, and subtracting moves us down. So vertical shifts are generally the easiest to conceptualize, and what we're doing here is simply adding a constant to the y-coordinates of our original function. Now in the next transformation, we will be modifying the x-coordinates, so it's good to remember what a function is. A function can be considered almost a set of grouping symbols. So in the order of operations, the function will act on the inputs, and then anything happening outside of that will be secondary. So we'll simplify stuff inside the function, and then the function will perform and do whatever it does to what's inside. And then finally we may multiply the result, or we may add or subtract to or from the result. So here we are calculating what the squaring does first, and then adding to. And for h of x, we are squaring first, so we're doing what f of x does, and then we're subtracting. Now in the next type of transformation, we're going to be changing what's happening inside of the function. So let's take a look at that. So here we see our second type of transformation, the horizontal shift. Now I am not going to use a specific function. I'm going to imagine a function f of x, and associated with that two functions g of x and h of x, where g of x is almost the same thing as f of x, except instead of f of x we have f of the argument x plus 1. So here I've already begun filling out our table. We've got some x values, and we see when we plug in those x values we get f of 0, f of 1, f of 2, f of 3. We get all of these y values, and I won't specify what those y values are. We might label them, call them y0, y1, y2, and so on, just for bookkeeping purposes. So we have these two options in terms of notation. We can discuss our y-coordinates either as f of the x that gave them to us, or we can talk about y's specifically, where these subscripts indicate what x gives us that y value. So we'll start with 0. If I plug 0 into this new function g of 0 would be f of 0 plus 1. In other words, f of 1. If we do the same thing with 1, g of 1 is identical to f of 1 plus 1. So plugging in our x value and adding 1 before we evaluate. So f of 2 is actually what that y-coordinate will be. Now we don't know what those numbers actually are, but we know that f of 1 is the output when x equals 1 in our original function. We'll keep going. G of 2, that would end up giving us 2 plus 1 inside the function f, which gives us f of 3, in other words, the y-coordinate of the original function when x is 3. And we can continue in this fashion. You'll start to see the pattern. If we plug in 4, what is that actually? Well, we always add 1. So g of 4 is really the same thing as f of 5, in other words, the y-coordinate when we plug 5 into the function f. Now, since we already know all of these points on the function f, we can tell how high these points are going to be with these slightly different x-coordinates. If we go in the other direction, g of -1 would be g of -1, or f of -1 plus 1, in other words, f of 0. So, we can keep going in that fashion. G of -2 is equivalent to f of -1. G of -3 would be equivalent to f of -2, which is y -2. Now if we look at the function h of x and do the same type of process, h of x subtracts 1 from the x value before the function f gets a chance to act on it. So h of 0 would actually be equivalent to f of -1. And h of 1 would be equivalent to f of 0. H of 2 would be equivalent to f of 1, and so on. And if we go in the other direction, h of -1, we're still subtracting 1 from that input, so that would be f of -2. H of -2 would be equivalent to f of -3, and so on. So the table is kind of nice, particularly if you have actual function formulas to work with. We do not, so let's just look at how the points are related. Here we have points on f of x, points on g of x, and points on h of x. Remember, if x is 0, then our function f gives us f of 0. If x is 0 and we plug it into the function g, we get f of 1. If x is 0 and we plug it into the function h of x, we get f of -1. If we plug 1 into our function, we get f of 1. If we plug 1 into the function g, we get f of 2. And plugging 1 into the function h gives us f of 0. So we know where, potentially given an actual function f to work with, We know the value of f of 0 and f of 1 and f of 2 and all of these. So this point, where x equals 1, is at the same height as the point on g of x, where x equals 0. So graphically, maybe our function f contains the point 1, 1, while the function g is going to contain the point 0, 1. So adding 1 inside of the function, adding 1 to x before the function gets a chance to act on it, results in a horizontal shift. And in fact, it results in a somewhat counterintuitive horizontal shift in the negative direction. Now, the opposite is true for the associated point at the same height on the function h of x. That point, at a height of f of 1, has an x-coordinate of 2, so that one is shifted to the right 1 unit, and that happened when we subtracted 1 from x inside the function. One nice way to remember this somewhat counterintuitive shift, remember if you add 1, you're shifting your original function to the left 1 unit, and if you subtract 1, you're shifting it to the right 1 unit in the positive direction. Think of daylight savings time. So if we originally, before daylight savings time, say that y equals t, here we are saying our actual time of day is given by t. So if t is 12, it's noon. If t is 9, it's 9 a.m. If t is 16, it's 4 o'clock in the afternoon. When daylight savings time rolls around, we add an hour to our clock. So we push the clock forward, and we actually lose an hour. So our function now would need a smaller t to give us the same time of day. And that's why everybody loses an hour of sleep when we shift our clocks forward. Now, if we subtract 1 from this, if I say y equals t plus 1, here we're in daylight savings time, and now we're going to roll our clocks back 1 hour. Now we're back to the original time. So y equals t, and this minus 1 now gives us an additional hour in the day. So we get an extra hour because we're subtracting an hour from our clocks. Another way that I like to think of this is from the perspective of the y value. Since what we're changing is the x values, if I am hoping to achieve f of 1, whatever that output is, I think about what the function g is. So f of 1 requires a 1 inside, and looking at what's inside of our function f, I have x plus 1, so my x value must be 0. It's 1 less than the x value that I'm shooting for. And that's why we see our horizontal shift to the left. We need a smaller x value in order to achieve the same y value because we are augmenting the x value inside. On the other hand, for the function h of x, if I would like to achieve a height of f of 1, well, my function h involves plugging x minus 1 into f. So I have a smaller quantity. I'm subtracting 1 from the input, so I need a larger input to achieve the same output. So my input needs to be 1 larger than it would normally be with my basic function f of x in order to arrive at the same output. And that is why our horizontal shift moves to the right when we subtract from x inside. So that is the idea behind the horizontal transformation, let's see that in action. So here we have two functions that are based off of one of our basic functions from the previous section. Now looking at these, the overall structure of these functions is both square root. So I'm square rooting x plus 3 in the first function, I'm square rooting x minus 1 in the second function. So each of these is going to be based off of the graph of the square root of x. So get out your graph paper. We're going to graph this one by hand. The square root function, again, you always want to have a few points that you know on the basic function. That'll make transforming it a little bit easier. So we're going to begin by graphing y equals the square root of x. And that graph passes through the point 0, 0, 1, 1, and 4, 2. Those are some nice points for us to work with. There is our basic graph. Now to graph f of x, we will recognize that this is going to look like the graph that we've drawn, but it's going to be shifted, and since what's changed is inside of the function, that will look like the square root graph. Since what's changed is inside of the square root, the shift is going to be horizontal. And since we are adding 3, we are going to move to the left 3 units. So I'll grab each of the points on the graph that I have pictured, and I'll move them to the left 3 units. So this point 0, 0 is going to move 1, 2, 3 over to negative 3, 0. 1, 1 will move to the left 1, 2, 3 over to negative 2, 1. And this point 4, 0 is going to move to the left, 4, 2 is going to move to the left 3 units to 1, 2. And every other point on the graph is going to do the same. And we'll see the same basic shape as we had. Alright, now if you're ever unsure of these, you can always plug in some points and make sure that this works. Remember the domain of the square root of x plus 3, I think we looked at this one in class last time, this is going to entail that x plus 3 never be negative. So our domain is all numbers greater than or equal to negative 3. So if I plug in negative 3, I get the square root of negative 3 plus 3, which is 0. Negative 2 gives me the square root of negative 2 plus 3, which is the square root of 1, which is 1. And this other point that we think we know about, if we plug in 1, the square root of 1 plus 3 will give us the square root of 4, which is 2. So we get all those points that we thought, negative 3, 0, negative 2, 1, 1, positive 2. And that's our translation. We would also like to graph g of x. So here we have f. G of x is going to look exactly the same as the original function y, the square root of x, except in this case we are going to shift to the right by 1 unit. So we'll move every one of those points right 1 unit and get the basic shape of our function to stay the same. So there we have the graph of g. So that's how you'll handle those sorts of horizontal transformations. First you need to identify what is the basic function that you're basing this off of, and then what is different inside. If there is a change inside, if we add or subtract from x, then we're going to have a horizontal translation either to the left or to the right. Now it's worth noting that we can combine transformations. And I'll show you an example of that now, while we only have a couple different types of transformations to worry about. So if I would like to graph f of x equals the square root of x plus 3 plus 2. Well, I would recognize that I'm going to take the square root of x, the graph of that, and I'm going to shift it to the right, to the left, 3 units, because inside I'm adding 3 to x, so I need to compensate by bumping all of my x values down by 3. And I'm also going to shift up 2 units. Another way to think of this is we are going to shift the graph of the square root of x plus 3 up 2 units. We already graphed this function, so we know what it looks like. And here I have f of x equals that function plus 2. So you don't always necessarily need to go all the way back to the beginning, figure out what your basic function is and do all of the transformations. If you know what part of the function looks like, you can apply the remaining transformations afterwards. So we already know what the square root of x plus 3 looks like. We just graphed it in the previous problem. 1, 2, 3, 0, negative 2, 1, 1, 2. And it has the shape of the square root graph, so that's the square root of x plus 3. Now all I need to do is shift up 2 units. So if I take each of those points and move them up 2 units, I will get the function that I am asked to graph. So here we have the square root of x plus 3 plus 2. Our next type of transformation involves a slightly different concept. Here we are going to see graphs reflected either across the x or the y-axis. Now, to cause a reflection of a point across the x-axis, so if I have a point AB, its mirror image across the axis will be located at A, negative B. To see that, we can plot a couple of points. Here we have our point AB. There are A units and B units vertically. Its mirror image across the x-axis will be located at A, negative B. So a vertical reflection can be achieved by making the y-coordinate negative. So if we have a function f of x, then every point on that graph can be described in this way, f of x. If we want to reflect across the axis, then the function should have a negative out front. Alright, so if we know what a graph looks like, for instance, we know what the graph of f of x equals x squared looks like, we can use that to graph the function g of x equals negative x squared. So recognize that this is negative f of x, since I have a negative outside of the original function. Now again, you can always come up with a table of values if you would like. We know a bunch of points on the graph of f of x, 0, 0, 1, 1, 2, 4. And in the negative direction, we see those symmetric points. So there we have our graph of f of x. The graph of g of x, if I take every y coordinate on this graph that I have, and I make it negative, well, 0, 0 can't really go anywhere. But 1, 1 will get reflected across and be at 1, negative 1 on my new graph. 2, 4, similarly, will reflect and give us the point 2, negative 4. And we'll see a symmetry about the axis on the other side. So here we can see how the generic point x squared has a counterpart at the same x coordinate, but the opposite y coordinate. And so this would be our graph of negative x squared based off our graph of x squared. Now, by similar reasoning, if I have horizontal reflection as my goal, if I have a point A, B on a graph of a function, and I wish to reflect that across the y-axis, how would I do that? Well, if I want it to be at the same height, its y-coordinate will be b. And if I want it to be on the opposite side of the y-axis, its x-coordinate will be the opposite of a. And so that's exactly how we achieve horizontal reflection when we're talking about functions. So given a function x, f of x, or a point on a function, the horizontal reflection can be achieved by plugging in negative x. Sorry. Little typo there. Alright, so our property, the graph of f of x, if we know what that looks like, f inverse, or f of negative x, will be the graph of f of x reflected horizontally. In other words, we'll reflect the graph that we know about across the y-axis. So let's use that idea. Let's graph, what's a good one? How about the square root of negative x? So we know what the square root function looks like. We plot our basic points to use as a template. 4, 2, and so on. So there is our starting graph. Now the square root of negative x, just to take a side trip, this graph has a domain when negative x is greater than or equal to 0. So remember, whatever is inside cannot be negative with these radicals. Now dividing by a negative, or multiplying by a negative, flips our inequality sign. So we see that x is less than or equal to 0. So our domain here is actually everything less than 0, or including 0. So this function, when we graph it, should only exist to the left of the y-axis. And that is exactly what we would achieve if we reflect this graph. So if I reflect the point 0, 0 across the y-axis, well, it's on the y-axis, so it's not going to go anywhere. But this point 1, 1, the x-coordinate is going to flip, and we'll get the point negative 1, 1. If we reflect the point 4, 2, its x-coordinate will become negative 4, its y-coordinate will remain the same. So the graph of the function we would like to graph, this is the square root of negative x. Now another way of thinking of the horizontal reflection, the mechanism which causes it, is a negative value attached to the x. In other words, inside of the function, instead of x I have negative x. So what does that do when we come up with a table? Well, if I plug in 0, I'm taking the square root of negative 0, which is the square root of 0, which is 0. If I plug in 1, then I would take the square root of negative 1, which is undefined. But if I plug in negative 1, that negative inside the function, built in now, cancels with the negative in the x value that I'm using. So we get the square root of positive 1, which is 1. And if I plug in negative 4, again, the negative and the negative of my x cancel, and I get the square root of positive 4, which is 2. So that negative inside now allows me to achieve the same output by inputting the opposite x value. On the original graph of our function, in order to get 2, we would have to plug in positive 4. Now we're plugging in negative 4. In order to achieve y equals 1 on the original graph, I had to plug in positive 1. Now I have to plug in negative 1 because I have a negative to compensate for. So very similar to the horizontal shifting, that negative now requires us to modify the x value in order to achieve the same y value. In particular, in this case, by making the x value negative, or opposite of what it would normally be. Our final type of transformation in this section is the vertical stretch or compression. Now I like to think of stretches and compressions as being the same mechanism. We are scaling our function. So what does that mean? Well, if we take the graph of a function f of x and we multiply the function by a constant, what changes? Well, if we plug in some x values and we evaluate them in our function, then we are going to multiply those x or those y values by that constant. So if I plug in 0, normally I would get f of 0, now I'm going to get c times f of 0. If I plug in 1, normally I would get f of 1, now I'm going to get c times f of 1. So I have all of the same x-coordinates as I do originally. The only difference appears to be in the y-coordinates. So if the point x, f of x, lies on the graph of our original function, then the point x, c times f of x, is on the graph of our new function. So what's happening? We're scaling the y values of the original function by a factor of c. So if c is a large number, we're going to stretch our y coordinates vertically. If c is a small number, if c is a half or a quarter, something along those lines, we're going to compress our function's graph vertically. All of our y-coordinates are going to get half as tall, or a quarter as tall. So let's graph, let's see, y equals the cube root of x. Say f of x equals the, let's say, 2 times the cube root of x. And g of x equals 1/2 the cube root of x. Here's some nice large graph paper. We're going to base all of these off of the basic function, the cube root of x, which we know passes through the point 0, 0, 1, 1, 8, 2, and is odd, so it's symmetrical about the origin. So we have these mirror image points on the opposite side. And so there is our cube root function. Try to connect it as smoothly as we can. Now, what is different about f of x? Well, every point is going to get stretched by a factor of 2. In other words, every point is going to be twice as tall. So the point 1, 1, the y-coordinate is going to get multiplied by 2 and move up to 1, 2. 8, 2 is going to be twice as tall. We'll get stretched up to 8, 4. 1, negative 1, negative 1. Our y-coordinate will also be multiplied by 2, so negative 1 times 2 puts us down at 1, negative 2. And our last point, negative 8, negative 2, if we multiply that y-coordinate by 2, that will stretch us down to negative 8, negative 4. Now, what about the origin? Well, if we have a point at a height of 0, and we multiply that y-coordinate by 2, we're going to end up with the same point. 0, 0 gets stretched, but it doesn't go anywhere because it's at 0. It's twice as tall, but twice as tall as 0 is still 0. So there is our stretched version of this function. And we can see how this differs from the vertical and horizontal shifts. I haven't moved my points uniformly. I haven't moved everything up or down. I have stretched every point relative to the point that I'm basing it off of. So 8, 2 rather. Becomes stretched to a height of 4. 1, 1 is stretched to a height of 2. And negative 1, negative 1 is stretched to a height of negative 2. I like to think of this as a factor or as a scalar rather than a stretch. It kind of confuses some folks to say stretch, especially when we might be stretching in the negative direction.